Reality is a master architect writing its own biography. The universe is not a silent, empty stage, but a brilliant and active historian, meticulously constructing the chronicles of its own existence. This is the profound mystery of time's secret architecture, a concept that will completely reshape how you see everything from the atoms in your hand to the distant galaxies. We are about to journey through cosmic blueprints, from the seething quantum foam to the vast filaments of the cosmic web, to uncover exactly how the universe encodes its past and engineers its future. By the end of this exploration, you will understand the hidden mechanisms that allow reality to document itself, a revelation that bridges the gap between physics and philosophy. How does a cosmos without a librarian manage to keep such a perfect, sprawling record of its entire life? And what does that tell us about our own role in this grand story? At the very first instant, the universe was a single point containing the entire cosmic blueprint. Within that initial seed of reality, every future event, every star, and every story was already encoded. This is not a metaphor. The fundamental laws of physics, the unchangeable rules of our cosmos, are the primary instruments of this self-recording. Think of constants like the speed of light or the strength of gravity as the permanent ink used to write the cosmic chronicle. Their precise values are not random. They are the exact settings required for a universe capable of building complex structures and ultimately remembering itself. Cosmologist Lee Smolin presents a fascinating theory called cosmological natural selection. He suggests that the laws of our universe are what they are because they are fine-tuned for the production of black holes, which could be the seeds for new universes. In this view, our cosmos is a product of a deeper evolutionary process, and its physical laws are its genetic code. This code, written at the beginning, predetermined everything. The specific ratio of dark energy to matter, for instance, was just right. If there had been slightly more dark energy, the universe would have expanded too rapidly for galaxies to ever form. Without galaxies, there would be no stars, no planets, and no stages upon which history could unfold. The very fabric of spacetime itself is the parchment for this grand story. But how does the empty stage itself facilitate the recording of events? The answer lies in a concept that might sound familiar: entropy, which is the measure of disorder in a system. The universe began in a state of incredibly low entropy, a condition of perfect order that set the arrow of time in motion. This relentless flow toward higher entropy, toward increasing disorder, is not just chaos. It is the engine of change. Every event, from the collapse of a star to the falling of a leaf, creates a unique and irreversible signature in the arrangement of matter and energy. This signature is information. The universe is not just experiencing history, it is meticulously cataloging it through every single interaction, writing its biography one irreversible change at a time. This river of time flows because of a fundamental cosmic rule, the second law of thermodynamics. At its heart, this law is about entropy, a measure of the universe's growing disorder. Think of a drop of ink spreading through a glass of water. It starts as a concentrated, ordered spot, but it will always spread out, mixing into a uniform, disordered state. The universe is doing the same thing on a grand scale. It began in a state of incredibly low entropy, an exquisitely ordered and compact configuration, and it has been moving toward greater disorder ever since. This relentless increase in entropy is what gives time its arrow, its undeniable forward direction. Without it, events would have no sequence, no before and after. A shattered glass could reassemble itself, and a star's explosion would be indistinguishable from its formation. There would be no plot, no cause and effect, and therefore no history to record. Physicist Sean Carroll frames this beautifully, suggesting that the early universe's low entropy state is the ultimate boundary condition that allows the story of our cosmos to even begin. It is the first page of the Cosmic Chronicle, but how did the universe get this incredibly ordered starting point? The leading theory points to cosmic inflation, a moment of fantastically rapid expansion in the very first instance. This event effectively ironed out any wrinkles, setting up that pristine, low-entropy state that launched the arrow of time we all experience. Now consider the life of a star. It forms from a collapsing cloud of gas, a process driven by gravity that increases the local order. But this comes at a cost, a tremendous release of energy, and a corresponding increase in the overall entropy of the universe. The star burns for millions of years, and when it dies in a supernova, it scatters newly forged heavy elements across space. That explosion is a massive, irreversible leap in disorder, and it leaves behind a permanent historical marker, the chemical fingerprints of its life and death now embedded in future planets and perhaps even in us. Could a universe exist without this arrow of time? It is a strange thought. In such a place, every interaction would be reversible. An event and its undo would be equally likely. There would be no narrative, just a chaotic jumble of moments with no direction or lasting consequence. It would be a cosmos without a story, unable to build its own history because it could never decide what happened next. This profound connection between time's arrow and the very possibility of history forces us to look deeper into the realm where the rules seem to blur, the quantum world. But the universe's record-keeping goes far deeper than the simple flow of time. It operates at the most fundamental level of reality, the quantum realm. Here, before anything is observed, particles exist in a haze of pure potential. An electron is not in one place, but in a superposition of many possible places at once. It is a blurry photograph of reality, a collection of overlapping stories waiting to be developed. So how does this cloud of possibilities crystallize into the single, solid history we all agree upon? The answer lies in a subtle but powerful process known as quantum decoherence. Think of a perfectly still pond. If you drop a single pebble, you see a clear set of ripples. This is like an isolated quantum system, its wave-like possibilities coherent and undisturbed. But now, imagine a rainstorm. The surface of the pond is struck by countless raindrops, each one creating its own tiny ripples. These ripples interact, crashing into one another, and the original, clean pattern is lost in a chaotic jumble. This is decoherence. The quantum world is constantly being bombarded by its environment, by stray photons, air molecules, and even the faint background radiation of the cosmos. Every single one of these tiny interactions acts like a raindrop, disrupting the delicate superposition and forcing the system to pick a single, classical state. The fuzzy photograph snaps into sharp focus. This is not a theory of conscious observation, but one of relentless interaction. The moment a quantum system touches its environment, it is measured, and a specific outcome is selected from the menu of possibilities. This selected outcome is then amplified, copied, and spread throughout the environment. Physicist Voyager called this process quantum Darwinism. Just as natural selection favors traits that are best at replicating, quantum Darwinism suggests that the states of reality which survive are the ones that are most robust, the ones that can be widely copied and recorded by their surroundings. The position of a chair, for instance, is objective because countless photons have bounced off it. each one carrying a tiny piece of information about its location out into the world. That information is replicated millions of times, making it a stable, classical fact. This is how potential becomes actual. It is the universe's mechanism for inscribing a single, definitive event into its timeline. The path a photon took was not predetermined, but the moment it struck a detector or even a dust particle, that interaction became a permanent entry in the cosmic ledger. So where does that leave our own act of looking at the world? Are we special observers causing reality to collapse? In this framework, we are not the cause, but simply a part of the environment's endless process of measurement and recording. Our consciousness is one of the most complex systems to receive and process these widely scattered records. When you see a tree, you are not forcing it into existence. You are simply accessing the information about the tree that has already been broadcast and solidified through decoherence, information carried by the light that has already interacted with it. This resolves a deep mystery, but it raises another, even more profound one. If every interaction creates a record, where is all this information stored, and can it ever be truly lost? If every interaction creates a record, a permanent entry in the cosmic ledger, then a monumental question arises. Where is this unimaginable library of information actually stored? The answer may be stranger than any fiction, written not in the volume of space, but on its very edges. Picture a room where every single object inside, every dust mote and beam of light, is perfectly described by a shimmering, complex code painted on the walls. This is the essence of the holographic principle, a revolutionary idea that redefines our concept of reality itself. Proposed by physicists Gerard T. Hooft and Leonard Susskind, this principle suggests our three-dimensional universe, with all its depth and richness, might be a projection from a two-dimensional surface at its boundary. We are, in a sense, living inside a cosmic hologram. The clues for this astonishing idea emerged from the most information-hostile place imaginable, a black hole. When matter falls into a black hole, it seems to vanish, erased from our universe. But this creates a paradox because, according to quantum mechanics, information can never be truly destroyed. So where does it go? The work of physicists Jacob Bekenstein and Stephen Hawking provided a stunning hint. They found that a black hole's entropy, which is a direct measure of its information content, is not proportional to its volume, as you might expect. Instead, it is proportional to the surface area of its event horizon. The event horizon, that point of no return, acts like a vast spherical hard drive. Every bit of information about what fell in is somehow encoded onto this two-dimensional surface. The three-dimensional interior is projected from the information stored on its two-dimensional boundary. This logic, born from the extremes of black hole physics, might apply to the entire cosmos. Our universe has its own boundary, the cosmological horizon, the absolute limit of what we can ever see. The holographic principle implies that the entire history of our universe, every event from the first star to your reading of this sentence, could be encoded on this vast spherical shell at the edge of everything. The three-dimensional reality we experience, with its passage of time and unfolding history, is the projected image, the holographic movie playing out from data stored on the cosmic screen. This suggests a fundamental limit to how much information any region of space can contain. The universe is not an infinite archive. It is a finite, if unimaginably large, data storage system with its entire story written on its skin. If our reality and its entire past are just a projection from a distant surface, what does that say about the nature of time itself? Is the flow of history we feel just an emergent property, an illusion generated by this cosmic encoding? The architecture of reality appears to be built on a framework of information, but for that information to form a coherent history, it needs a scaffold, a great cosmic structure to give it form and sequence. Scattered across the emptiness, the universe constructs its grandest libraries. These are not built from paper and ink, but from galaxies themselves, strung along immense, glowing filaments that stretch for hundreds of millions of light years. This cosmic web is the universe's ultimate memory palace, a permanent, three-dimensional fossil of its own explosive birth. When powerful telescopes like those in the Sloan Digital Sky Survey map the positions of millions of galaxies, they reveal this intricate architecture, a spiderweb of stellar cities against the void. This vast pattern is not random. It is the amplified echo of the universe's first moments. In the primordial fireball, the cosmos was not perfectly smooth. It was textured with tiny quantum fluctuations, minute differences in density that were mere whispers in the fabric of space-time. Then, in a fraction of a second, the period of cosmic inflation occurred, stretching these microscopic wrinkles to proportions beyond comprehension. Those tiny density variations became the seeds for everything, the gravitational anchors around which all future structure would form. The specific pattern of the cosmic web we observe today, the precise placement of each filament and the vast emptiness of the voids between them, is a direct imprint of that original quantum noise. It is a baby picture of the cosmos frozen in space for us to decipher. By reading this galactic map, scientists can work backwards. The spacing of galaxy clusters tells us about the push of dark energy and the gravitational pull of dark matter, the two invisible forces that have sculpted the narrative of cosmic evolution. But these structures are far more than passive relics. They are dynamic engines of history. A galactic filament is a river of gas and stars, a highway feeding material into the dense nodes where galaxy clusters collide and merge. This constant flow of matter is what triggers the birth of new stars and the explosive deaths of old ones. Within these stellar factories, the simple elements forged in the Big Bang are cooked into heavier atoms, the very stuff of planets and life. The cosmic web does not just remember the past, it actively uses that information to build the future. It is the universe's way of channeling its primordial potential into the specific, localized events that write the next chapter of its story. And at the heart of that story, within the swirling gas of these galaxies, the most dramatic transformations occur, where stars are born and die in cycles of cosmic alchemy. Deep within the furnaces of ancient stars, the universe learned to write with a new alphabet. A star is far more than a distant light. It is a cosmic alchemist, a factory that forges the very elements of history itself. This process is called nucleosynthesis, and it is the primary way our universe built the complex chemical diversity needed for planets, for oceans, and for us. In the beginning, after the Big Bang, the cosmos was a simple soup of the lightest elements, mostly hydrogen and helium. It was a blank page. Then the first stars ignited. These primordial giants, known as population 3 stars, were behemoths that lived fast and died young. Their immense gravity crushed hydrogen atoms together, fusing them into helium, and then, in a cascading chain of nuclear reactions, they forged the first heavy elements like carbon and oxygen. They were the universe's first authors, scribbling the opening chemical chapters with their own fiery lives. The iconic words of Carl Sagan echo here with profound truth. We are made of star stuff, but how exactly does the stuff of stars become the stuff of us? The journey is a dramatic, multi-stage saga. Inside any typical star like our Sun, a relentless battle rages between the inward crush of gravity and the outward push of nuclear fusion. For most of its life, a star fuses hydrogen into helium. When the hydrogen runs low, the core contracts, heats up, and begins fusing helium into carbon. In more massive stars, this process continues in successive shells like the layers of an onion, creating progressively heavier elements all the way up to iron. But iron is a dead end. Fusing iron does not release energy, it consumes it. With its energy source cut off, the star's core collapses in a heartbeat. This catastrophic collapse triggers a titanic rebound, a supernova explosion so powerful that it outshines an entire galaxy. In that unimaginable inferno of pressure and neutrons, in a few fleeting seconds, every element heavier than iron is forged. Gold, silver, lead, uranium, the iodine in our bodies, all are created in these violent stellar deaths. The explosion then hurls this newly minted elemental richness out into the surrounding space, a cloud of stardust that will one day coalesce into new stars, new planets, and new possibilities. This chemical enrichment is the universe's way of passing down its legacy. The specific mix of elements found in a star acts as a permanent historical record. A star rich in iron, for example, tells astronomers that it was born from a cloud of gas that was itself seeded by the debris of many prior supernovae. The iron in your blood was once the core of a massive star that lived and died billions of years ago, long before our sun was even a glimmer in the galaxy. The calcium in your bones was baked in the heart of a red giant star. We are walking archives of ancient stellar histories. This elegantly preserved record leads to an inevitable next step. Once a cloud of gas is enriched with these heavy elements, the stage is set for the universe to build not just new stars, but intricate planetary systems around them. Our own planet is a billion-page autobiography written in stone. The ground beneath your feet is not just dirt and rock, it is a meticulously layered chronicle, a geological archive that preserves the local history of our cosmic neighborhood. This is the principle of planetary geology, where every world becomes a library of its own past. The primary method for reading this cosmic book is called stratigraphy, the simple but profound idea that in an undisturbed sequence of rock layers, the oldest layers are at the bottom and the youngest are at the top. By reading this vertical timeline, scientists can decipher billions of years of Earth's history, from the first formation of continents to the rise and fall of ancient life. But to turn these relative pages into a precise calendar, we need a clock. That clock is radiometric dating. It works by measuring the natural decay of radioactive elements trapped within crystals when a rock forms. Think of a radioactive isotope, like a specific type of uranium, as an hourglass with a fixed, known rate of sand flow. When a mineral crystallizes, it locks in the uranium. Over millions of years, that uranium steadily decays into lead. By carefully measuring the ratio of remaining uranium to the accumulated lead, scientists can calculate the exact age of the rock, turning a silent layer into a dated entry in the planetary ledger. This technique reveals the exact timeline of our world, proving the Earth is 4.54 billion years old. Sometimes, the universe inscribes its history with a sudden, violent pen. A perfect example is found in a thin, global layer of clay known as the KPG boundary. This layer is dramatically enriched with the element iridium, which is rare on Earth's surface but common in asteroids. This iridium-rich stripe in the rock record, found all over the globe, is the permanent, undeniable signature of a colossal asteroid impact 66 million years ago. That single cosmic event, a day of fire and global winter, was directly recorded in the geology of our planet, marking the mass extinction that ended the age of the dinosaurs. This is not a story confined to Earth. The stark, red surface of Mars is etched with its own geological memories. Orbiting spacecraft have photographed vast, dried-up riverbeds and sedimentary layers that could only have been deposited by persistent, flowing water. These features are a frozen narrative telling the story of a warmer, wetter Mars with lakes and perhaps even an ocean, a chapter in the planet's history that ended billions of years ago. Each planet and moon in our solar system holds similar records, preserving the specific conditions of its own unique past. But for the most pristine, unaltered archives of the solar system's violent infancy, we must look to the frozen time capsules drifting in the void. Drifting in the deep freeze of space, far from the warmth of stars, are the original, unopened letters from the dawn of our solar system. Asteroids and comets are the leftover construction materials, the pristine building blocks that never formed into planets. Because they have remained largely unchanged for 4.5 billion years, they offer a perfectly preserved snapshot of the chaotic nursery our solar system once was. Think of a carbon-rich asteroid like a frozen time capsule, sealed at the moment of its creation. These ancient rocks, known as carbonaceous chondrites, are particularly precious. They are cosmic treasure chests found to contain a rich mixture of water and complex organic molecules, the very chemical precursors to life itself. This tells us that the fundamental ingredients for biology were not a late addition to our cosmic neighborhood, but were present from the very beginning, baked into the foundation of our planetary system. Missions like NASA OSIRIS-REx are essentially cosmic archaeologists, traveling to these primordial relics to bring pieces of that ancient past back to Earth. The spacecraft performed a delicate touchdown on the asteroid Bennu, a dark, carbon-rich world that has witnessed the entire history of our solar system. By retrieving a sample from its surface, scientists aim to hold a piece of that original construction material in their hands, analyzing it for clues about how water and organics were distributed in the early solar system. But the historical records locked within these objects go even deeper than their chemistry. The very atoms themselves carry a stellar signature. Within meteorites that have fallen to Earth, scientists can measure precise isotopic ratios. Isotopes are different versions of the same element with varying numbers of neutrons in their nuclei. The specific mix of these isotopes acts as a fingerprint telling a story that predates our Sun. These patterns were set by the nucleosynthesis processes that occurred inside the giant stars that lived and died before our solar system was even a cloud of dust. The iron in an asteroid sample can tell us about the specific type of supernova that seeded our local region of space with heavy elements. Comets add another layer to this ancient archive. These icy travelers spend most of their lives in the distant, frigid Oort cloud, only occasionally falling inward toward the Sun. Each visit is like a historian arriving from the outermost, coldest vault of the solar system, delivering material that has been kept in a state of perfect preservation for eons. As a comet nears the Sun and its ices begin to vaporize, it releases this primordial gas and dust into space, giving us a direct sample of the conditions in the outer solar system's earliest days. Studying these celestial time capsules is like reading the original architectural blueprints and the list of raw materials for our entire planetary neighborhood. This process reveals a profound and elegant cycle, the ultimate cosmic recycling program, where the remnants of one era become the foundation for the next. The universe operates the ultimate recycling program where nothing is ever truly lost, only transformed. This grand cycle of matter turns the ashes of dead stars into the building blocks for new worlds, weaving the past directly into the fabric of the future. The raw material for this endless rebirth is the interstellar medium, a vast and diffuse ocean of gas and dust that fills the spaces between stars. It is a cosmic junkyard and a nursery all in one, composed of the ejected remains of countless supernovae and the gentle outflows from aging red giants. Within this murky expanse, the history of the galaxy is written in a complex chemistry of hydrogen, helium, and enriched with heavier elements like carbon, oxygen, and iron. To see this process in action, we can look to the Orion Nebula, a stellar maternity ward visible through a simple backyard telescope. The glowing clouds of Orion are not just a beautiful sight, they are a dynamic factory. Intense radiation from newborn stars is sculpting the surrounding gas, compressing parts of it and triggering the collapse that will lead to the birth of even more stars. These brilliant young stars are literally built from the graves of their ancestors. The catalyst for this star birth is often violence. When a massive star ends its life in a supernova, it does not die quietly. The explosion sends a colossal shockwave racing through the interstellar medium at millions of miles per hour. This shockwave acts like a cosmic plow, slamming into nearby clouds of gas and dust. It compresses the material, creating dense, knotty regions where gravity can finally overcome outward pressure and begin its work of collapse. A new solar system is born from this chaos. Within the swirling disk of material that forms around a fledgling star, dust grains made of silicates and carbon compounds begin to stick together. They form pebbles, then rocks, then planetesimals, and finally planets. Every atom in this new system carries a legacy. The iron in the core of a rocky planet was forged in the heart of a long-dead massive star. The carbon that forms the basis of organic chemistry was likely created in a red giant. The gold in a planet's crust was produced in the spectacular collision of two neutron stars, an event that occurred perhaps billions of years before our sun even ignited. Our own solar system is a testament to this mixed heritage. Isotopic analysis of meteorites reveals that our sun and its planets formed from a cloud that was seeded by material from at least two different types of supernova. We are not the product of a single stellar ancestor, but a collective, a melting pot of cosmic histories. This means the universe's story is not a straight line from a beginning to an end. It is a complex, braided narrative where the end of one chapter provides the opening words for the next. The cycle is clear, from star dust to planet dust, and eventually to us. But how does a living, breathing planet like Earth then take this inherited material and begin writing its own unique entries into the cosmic chronicle? Life itself became the universe's most prolific author. Far from a passive result of cosmic conditions, the biosphere emerged as a powerful geological force, actively rewriting the planet's story. This is the profound shift captured by the Gaia hypothesis, which proposes that life and its physical environment form a complex, self-regulating system. Life does not merely adapt to the world, it constantly remakes it. The most dramatic example of this began over 2 billion years ago with organisms too small to see. Cyanobacteria, the first photosynthetic microbes, learned to harness sunlight for energy, and their waste product was a gas that was pure poison to most other life at the time, oxygen. This was the Great Oxidation Event, a planetary revolution triggered by biology. The evidence is permanently stamped into the rock record in the form of banded iron formations. These stunning, striped layers of red and gray rock represent a global chemical battle. As cyanobacteria pumped oxygen into the oceans, it reacted with dissolved iron, causing the iron to rust and settle to the seafloor in massive deposits. These geological bands are the literal pages of a history book, recording the moment life forever altered the chemistry of its world. This was not a gentle adjustment. It was a catastrophe for the ancient, oxygen-hating life forms, causing a mass extinction. Yet from that crisis, a new, more complex world was born, paving the way for oxygen-breathing life. Life's inscriptions go far beyond a single event. The very soil beneath our feet is a biological creation, a living matrix teeming with fungi and bacteria that break down rock and organic matter, building a fertile crust that supports all terrestrial life. Forests influence rainfall patterns, and marine organisms regulate the carbon cycle, subtly modulating the global climate over eons. The fossil record is the most direct library of this biological chronicle. Each fossil is a snapshot, a data point in the epic narrative of evolution and extinction. The sudden absence of dinosaur fossils after the KPG boundary layer tells a story of cosmic intervention, while the gradual emergence of mammalian forms writes a new chapter of diversification. Life, therefore, is a co-author of planetary history. It takes the raw materials provided by stellar explosions and asteroid deliveries and uses them to build ever more complex systems, inscribing its own triumphs and tragedies directly into the planetary archive. This raises a pivotal question about our own species. If cyanobacteria could trigger a geological era, what chapter is humanity writing with its own unprecedented power? Humanity has now become a geological force, laying down a new stratum of planetary memory. We are constructing the technosphere, a global membrane of cities, farmlands, satellites, and digital networks that is fundamentally altering Earth. This is the universe through the lens of our own intelligence, engineering a radical new method for recording its story. Geologists propose we have entered a new epoch called the Anthropocene, a chapter in Earth's official timeline defined by the overwhelming impact of a single species, us. The evidence for this new era is being cemented into the rock itself, creating permanent markers that will be readable for millions of years. Think of the thin, global layer of plastic particles now settling on the seafloor and embedding in sediments, a signature of our civilization that will never fully vanish. Concrete has become a dominant rock type, its volume already exceeding the total living biomass on the planet. And then there are the artificial radionuclides, the unique atomic fingerprints of nuclear testing that settled across the globe in the mid-20th century. These radioactive elements, like plutonium, do not exist in nature and will serve as an indelible golden spike in the geological column, a stark line dividing one human age from the next. But our record-keeping has burst beyond the atmosphere. The Voyager spacecraft, now sailing through interstellar space, carry golden records etched with sounds and images of Earth. They are cosmic time capsules, bottles thrown into the galactic ocean, carrying a chapter of our planet's history to distant stars. Closer to home, our digital cloud represents an entirely new form of cosmic memory. The immense repositories of data we generate every day, from scientific archives to social media, form a fragile yet vast nervous system for the planet, a living chronicle of a technological species. The emergence of the technosphere demonstrates that the universe's architecture for building history is not static. It can evolve, incorporating intelligent agents that create complex, non-biological records at a breathtaking pace. But this new layer raises a profound question about longevity. How will these technological memories, from skyscrapers to server farms, withstand the test of deep time? The universe's oldest records are written in stone and starlight, but ours are written in silicon and steel, materials far more vulnerable to the relentless march of entropy. We are all cosmic archaeologists, sifting through layers of time with telescopes as our tools. The night sky is not a single snapshot but a sprawling dig site, where every point of light arrives from a different era in the universe's past. This is possible because light does not travel instantaneously. It has a finite speed. When we observe a galaxy 1 billion light-years away, the light entering our telescope has been on an epic journey for 1 billion years. We are not seeing that galaxy as it is today, but as it was when dinosaurs roamed the Earth. We are literally looking back in time, The Hubble Space Telescope's deep field images provide the most stunning evidence for this. By staring at a seemingly empty patch of sky for days, Hubble collected photons that had been traveling for over 13 billion years. The result was not darkness, but a vibrant tapestry of thousands of galaxies, each one a teenage portrait of the early universe caught in the act of formation. This is cosmic archaeology in its purest form, excavating the universe's childhood by simply looking out into the void. But how do we know the distance, and therefore the age, of these faint smudges of light? The universe itself provides the ruler through a phenomenon called redshift. As the fabric of space expands, it stretches the wavelengths of light traveling through it. Think of the sound of a passing ambulance siren, how its pitch drops as it moves away from you. Light behaves in a similar way. The faster a galaxy is receding from us due to the cosmic expansion, the more its light is stretched toward the red end of the spectrum. By measuring this redshift with exquisite precision, astronomers can calculate not only how far away a galaxy is, but also how long its light has been traveling to reach us. This turns the entire sky into a multi-layered historical document. We can directly compare ancient, redshifted galaxies from the deep past with mature, nearby galaxies to reconstruct the entire story of cosmic evolution. We can even perform this archaeology within our own celestial home. Globular clusters, dense spheres of hundreds of thousands of ancient stars that orbit the Milky Way's halo, are like living fossils. By studying the ages of their stars, which are among the oldest in the universe, we can piece together a timeline of our galaxy's violent assembly, a story of mergers and acquisitions over billions of years. The universe's history is not locked away in a vault. It is projected all around us, a silent film playing on the dome of the sky. But this magnificent library, written in light, faces a formidable enemy. The same force that makes history possible, the relentless growth of entropy, also threatens to erase it all in the distant future. Every great story faces the threat of being forgotten, and the universe's epic is no different. The very force that gives time its arrow and allows history to be written, entropy, is also the force that will ultimately erase it. Think of a sandcastle on a beach, an intricate structure painstakingly built. The incoming tide does not care about its beauty or complexity. It simply washes over it, smoothing the towers and filling the moats until the castle is once again indistinguishable from the endless, flat sand. This is the inevitable fate of all cosmic memory in a universe governed by the second law of thermodynamics. As the cosmos expands and ages, it relentlessly marches toward a state of maximum entropy, a final, lukewarm equilibrium where all energy is evenly distributed. In this distant future, known as the heat death of the universe, every energy gradient will be flattened. Stars will have long since burned out, their ashes scattered and cooled. Black holes will have evaporated through Hawking radiation. Galaxies will be ghostly, diffuse clouds of subatomic particles drifting infinitely far apart. In this state, there are no temperature differences to drive engines, no concentration of matter to form new structures, and no meaningful events to record. A history book requires a contrast between the past and the present, but in this ultimate equilibrium, there is no contrast left. The universe's biography, written over billions of years, will slowly fade into a uniform, featureless blank page. This creates a profound paradox. How can the universe be building a permanent history if the ultimate laws of physics guarantee its eventual erasure? The brilliant physicist Roger Penrose has proposed a truly mind-bending answer, a model called Conformal Cyclic Cosmology. He suggests that the universe does not have a single, final end. Instead, in the far, far future when the cosmos has expanded into nothing but a sea of low-energy photons and massless particles, the concept of scale and distance becomes meaningless. In this strange, smooth state, the universe can effectively connect to a new Big Bang, a new cycle of cosmic birth. The information from the previous eon, our entire universe, is not technically destroyed but is transformed. It is lost to the world of matter and forces as we know them, but its imprint, its gravitational fingerprint, might carry over to influence the next cycle. It is a cosmic whisper passed from one age to the next. Other theories, like the holographic principle we discussed earlier, offer a different kind of solace. They argue that information is never truly lost, it is merely translated. Even as a three-dimensional star collapses into a black hole, the information about its composition is not destroyed. It is encoded onto the two-dimensional surface of the event horizon. In a similar way, as the entire universe approaches its heat death, the sum total of its history, every event and memory, could be preserved on the cosmological horizon. The story becomes permanently filed away in the universe's ultimate archive, even if there is no one and nothing left inside to read it. This is a sobering conclusion for our cosmic narrative. The universe may be a brilliant architect, but it is building its magnificent cathedrals of memory on a foundation of sand, destined to be washed away by the relentless tide of time. Yet, these speculative models offer a glimmer of hope, a suggestion that history might somehow transcend a single lifetime of a cosmos, echoing into the birth of the next. If the universe's story can indeed be reborn, what does that imply about the very nature of time and existence itself? The universe may not have just one story to tell, but an infinite series of them. This is the principle of the cosmic phoenix, the breathtaking idea that our entire cosmos is part of an endless cycle of birth, death, and rebirth. In this grand vision, the universe's history is not a single, linear book with a final page, but an eternal, multi-volume epic where each ending sets the stage for a new beginning. We have already touched upon Roger Penrose's conformal cyclic cosmology, a theory where the distant, featureless heat death of one universe becomes the smooth, high-energy starting point for the next Big Bang. But there is another compelling model born from the depths of string theory, known as the ekpyrotic scenario. Imagine our three-dimensional universe as a vast, floating sheet, or a brain, existing alongside another in a higher dimensional space. The Big Bang, in this view, was not a violent explosion from a singularity, but a majestic, cyclical collision between our brain and a neighboring one. This cosmic contact injects immense energy, resetting and reheating our universe, beginning a new cycle. The profound implication of both these models is that information from a previous cycle might not be completely annihilated. It could leave a faint, ghostly imprint on the newborn cosmos. Penrose has famously argued that he has found such a signature in the cosmic microwave background, the ancient light from the early universe. He points to strange, concentric circles within this radiation, which he interprets as the gravitational shock waves from supermassive black hole collisions that occurred in the universe that existed before our own. If verified, these circles would be the ultimate historical artifact, a fossilized echo from a prior cosmic age. This cyclical framework fundamentally transforms the nature of cosmic history. Instead of a one-time event with a fixed set of rules, the universe could be engaged in a form of cosmic evolution. The physical constants and laws we take for granted, like the strength of gravity or the mass of an electron, might not be immutable. They could be the result of evolutionary processes that unfolded over countless cycles, slowly tuning the universe for greater complexity or stability with each iteration. The universe would not just have a history, its very rulebook would have a history. This shifts our entire perspective from a single, linear narrative to an eternal, perhaps ever-changing epic. But how can the chaotic, probabilistic nature of the quantum world possibly survive such a grand cosmic reset to influence a new cycle? The answer may lie in the silent, seething energy of empty space itself. The apparent emptiness of space is a grand illusion. Between the stars and galaxies lies the quantum vacuum, a seething sea of potential that is anything but empty. This is the fundamental canvas, the substrate of possibility upon which the entire history of the universe is painted. According to quantum field theory, every cubic centimeter of so-called empty space is a turbulent ocean of activity. Virtual particles, pairs of matter and antimatter, constantly flicker into existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and vanishing. This endless dance of creation and destruction is not just a theoretical curiosity, it is the engine of reality itself. These quantum fluctuations are the raw material for everything. In the first instance of the cosmos, the period of cosmic inflation stretched these microscopic ripples in the quantum field to astronomical proportions. Those tiny, random fluctuations became the seeds for all structure, the gravitational blueprints for galaxies, stars, and ultimately, us. The specific pattern of the cosmic web we observe today is a direct, amplified imprint of that primordial quantum noise. The vacuum is not just a stage, it is an active participant with its own energy and structure. This is what physicists call dark energy, or the cosmological constant, a fundamental energy inherent to empty space that is driving the accelerated expansion of the universe. The properties of this vacuum energy are not arbitrary. They determine the very constants of nature, the unchangeable rules like the strength of gravity and the speed of light that allow for a cosmos capable of building complex histories. A different vacuum state would mean a different set of physical laws, a different universe with a completely different narrative, one that might be incapable of forming atoms or stars. A perfect example of this shaping power is the Higgs field. This invisible energy field permeates all of space, and as particles move through it, they interact with it, acquiring the property we call mass. Without the Higgs field, electrons would have no mass and atoms could not form. There would be no chemistry, no planets, and no life. The Higgs field is a vacuum property that decided, in the earliest moments, what kind of story our universe could even tell. This raises a profound question about the architect itself. Could the quantum vacuum, the foundation of all reality, have its own history? Could its state be the result of a prior cosmic event, a frozen memory from a time before our Big Bang? The answer might lie in the most speculative and staggering of ideas, the multiverse. Our universe may be just one book in an infinite cosmic library. This is the Multiverse Hypothesis, a staggering idea that redefines the very meaning of history. Within this grand library, each volume is a self-contained universe, complete with its own physical laws and its own unique, sprawling narrative. Our story, from the Big Bang to the rise of life, would be just one tale among a near-infinite collection. The leading scientific framework for this is the theory of eternal inflation. Picture the primordial cosmos as a constantly expanding, high-energy substrate, a roiling ocean of spacetime. Within this ocean, pockets of stability can suddenly form, like bubbles appearing in a pot of boiling water. Each of these bubbles stops inflating internally and crystallizes into its own separate universe, with its own random set of physical constants. In one bubble universe, the force of gravity might be 10 times stronger, causing stars to burn out in a fleeting million years. In another, the nuclear forces might be too weak for atoms to ever stick together, resulting in a cosmos of scattered particles that can form no structures at all. These universes would have no history as we understand it, no chronicle of evolving complexity, because their fundamental rules forbid it. Our universe, with its specific, finely tuned constants, is simply the volume we happen to inhabit. What we call our history is not a predetermined script, but one specific narrative path that was actualized from an endless sea of possibilities. The architecture of time and history is therefore not a singular, universal plan. It is a localized outcome, a single method of self-historicization that works within our particular set of rules. The challenge is profound. These other histories are likely forever locked away from us, their pages unreadable across the unimaginable divides between realities. Yet the concept alone forces a radical shift in perspective. It suggests that the universe is not building one history, but is a factory for generating all possible histories, a meta-reality of boundless potential. This leads to a final, deeply personal question. If the cosmos is a vast, self-documenting system, and we are a part of it, what is our role in reading this cosmic record? How does our own consciousness interact with this grand architecture of memory? That ancient philosophical question echoes through the corridors of physics. If a tree falls in a forest with no one to hear it, does it even make a sound? Or more fundamentally, did the event even happen in a definite way until a conscious mind registered its outcome? This leads us to one of the most provocative ideas in all of science, the notion that consciousness itself might be the final instrument that solidifies reality, turning potential into actual history. At the heart of this mystery lies the Copenhagen interpretation of quantum mechanics, formulated by figures like Niels Bohr and Werner Heisenberg. It proposes that a quantum system, like an electron, exists in a blurry superposition of all possible states until it is observed. The very act of measurement, of looking, is what collapses this wave function, forcing the universe to choose one specific, concrete outcome from the menu of possibilities. In this view, the observer is not separate from the system, but an active participant in its final definition. The universe's history is not just recorded, it is literally authored through the process of observation. This concept was pushed to its logical and deeply strange conclusion with a thought experiment known as Wigner's friend, proposed by physicist Eugene Wigner. Imagine a scientist in an isolated laboratory measuring a quantum particle, which collapses into a specific state for him. But for you, outside the lab, the entire system, including your friend and his measurement, remains in a superposition. Your observation is what finally collapses the entire entangled reality, deciding what your friend actually saw. This seems to create a chain of observation, raising the question of where it ultimately ends. Does it require a final, cosmic consciousness to pin down all of reality? Most physicists today find this deeply unsatisfying and point back to the process of quantum decoherence we explored earlier. In that modern framework, consciousness is not special. The environment itself acts as a continuous observer. The moment a quantum system interacts with a single photon or a dust particle, its fuzzy superposition is destroyed and a definite history is recorded. There is no need for a human mind to be involved. The tree falling in the forest creates a sound wave that interacts with the air and the ground, irrevocably changing them. The event is solidly logged into the cosmic ledger long before any hiker arrives on the scene. Yet, even with this more physical explanation, a profound philosophical question lingers. If the universe is building its own history, what is the role of a species that emerges within it, capable of not just being recorded, but of reading the record? This is the participatory anthropic principle, the idea that our conscious observation, while not causing collapse, is a fundamental part of the cosmic process. Our act of looking at the stars, of digging up fossils, of analyzing the cosmic microwave background, is a new, reflexive layer of cosmic record-keeping. The universe, through us, has begun to contemplate itself. We are not passive spectators. Our scientific inquiry creates a new kind of historical artifact, a self-aware chronicle. The data from the Hubble Space Telescope is not just light from a distant galaxy. It is the universe's story being consciously decoded and understood by a part of itself. This creates a remarkable feedback loop where the history being built then influences the conscious agents who are, in turn, adding new chapters to that very history. So how do we, as these conscious beings, actively contribute to this grand historical project? The answer lies in the future we are now helping to write, a future of cosmic archaeology that extends far beyond our own planet. For over a century, our cosmic movie was a silent film. We could see the universe in all its visual splendor, from swirling galaxies to exploding stars, but we were deaf to its deepest rhythms. That all changed with our newfound ability to listen. Gravitational waves are the sounds of space-time itself ringing like a bell. They are ripples in the very fabric of reality, generated by the most violent events in the cosmos, and they carry a pristine, unaltered story across billions of light years. This is not a metaphor. In 2015, the LIGO Observatory made the first direct detection of these waves, confirming a century-old prediction by Einstein. The signal came from a collision that occurred 1.3 billion years ago between two black holes 30 times the mass of our Sun. In their final moments, these monstrous objects whipped around each other at nearly the speed of light, churning the space-time around them and sending a shrieking gravitational wave out into the universe. This was a clean, direct recording of an event that was completely dark to every telescope on Earth. Unlike light, which can be scattered, absorbed, or distorted by interstellar gas and dust, gravitational waves pass through matter almost completely unaffected. They bring us a signal straight from the source, a perfect historical document of a cataclysm that left no other trace. This allows us to study the hidden population of black holes and neutron stars, objects that often reveal themselves only through these space-time tremors. The future of this new sense is even more thrilling. Projects like the space-based LISA Observatory will open up a much lower frequency band, allowing us to hear the slow, cosmic dance of supermassive black holes as they merge at the hearts of galaxies. These events are the foundation of galactic evolution, and by listening to them, we will be hearing the very history of how the largest structures in the universe were assembled. Gravitational wave astronomy has added a soundtrack to our silent film, revealing the dynamics and violence that were previously hidden from our view. But if we can now hear the universe, what other elusive messengers are carrying its history right through us, completely unseen? Ghosts are passing through you right now, trillions of them every second, leaving no trace. These are neutrinos, the universe's most elusive messengers. With almost no mass and no electric charge, they barely interact with anything. A neutrino can fly straight through a light year of solid lead without slowing down. This ghostly nature, once a frustrating puzzle, has become one of our most powerful tools for cosmic archaeology. Because they ignore almost everything in their path, neutrinos bring us a pure, unedited signal from the deepest, most violent places in the cosmos. To catch these phantoms, we must build traps on an epic scale. In a mine deep under a Japanese mountain, the Super Kamiokande detector waits. It is a colossal tank filled with 50,000 tons of ultra-pure water, lined with 13,000 golden eyes, sensitive light sensors that watch for a rare event. Once in a great while, a neutrino passing through the water will strike an atomic nucleus, producing a faint, telltale flash of blue light called Cherenkov radiation. This is how we see the unseeable. Another detector, Ice Cube at the South Pole, uses a cubic kilometer of ancient, pristine Antarctic ice as its medium. It has frozen over 5,000 sensors deep within the ice, waiting for those same rare flashes from neutrinos that have traveled from the far reaches of the universe. What stories do these ghosts tell? They are our only direct line into the heart of a living star. The neutrinos we detect from the Sun are not produced at its surface, but in its core where nuclear fusion rages. Photons of light take thousands of years to bounce their way out from the center, but neutrinos, ignoring the dense plasma, escape in just over 8 minutes. When we detect a solar neutrino, we are receiving a live broadcast from the very engine of our star, a snapshot of its nuclear furnace that is only 8 minutes old. Their value becomes even more dramatic in stellar death. In 1987, a star went supernova in a nearby galaxy. Hours before its light reached Earth, a handful of detectors around the world registered a brief, precious burst of 24 neutrinos. This was the death scream of the star's core, a direct transmission of its catastrophic collapse into a neutron star. The light from the explosion arrived later, as the shockwave finally blasted through the star's outer layers. Those few neutrinos confirmed our deepest theories about how massive stars die. Today, we are detecting neutrinos from even more monstrous sources, like the blazing cores of active galactic nuclei, where supermassive black holes devour matter and spew out colossal jets of energy. These cosmic ghosts provide a live feed from the universe's most powerful engines, a historical record that is immediate and unfiltered. We now have light to see the universe, gravitational waves to hear it, and neutrinos to feel its most hidden, energetic heartbeats. How do we begin to synthesize all these different streams of history into a single, coherent story of everything? We are building a digital twin of the cosmos. All the light, radio waves, and gravitational signals we have ever captured are converging into vast supercomputers, creating a dynamic simulation of the universe's entire history. This is data cosmology, a revolutionary field where computation becomes our ultimate time machine. Projects like the Illustris TNG simulation do not just create pretty pictures, they run the entire cosmic story from the first moments after the Big Bang to the present day. These simulations are staggeringly complex, weaving together the laws of gravity, the turbulent flow of galactic gases, the influence of dark matter, and even the effects of magnetic fields and supermassive black holes. They are virtual universes born from code that grow their own galaxies and weave their own cosmic webs over billions of simulated years. The true power of this digital reconstruction lies in comparison. Scientists run the simulation with our best understanding of physics baked in, and then they compare the final result, a universe at 13.8 billion years old, with the actual data from our telescopes. Does the virtual cosmos produce the same mix of spiral and elliptical galaxies? Do the stars within them have the right chemical compositions? Is the large-scale structure of the cosmic web a match? If the simulation produces a universe that looks profoundly different from our own, it is a powerful clue that our theories are missing a crucial piece of the puzzle. This process is a profound collaboration between the cosmos and our consciousness. The universe provides the raw historical data, the immutable record of what actually happened, and we provide the interpretive framework, testing our models against its grand narrative. The digital universe becomes a new, interactive archive, a working model of reality's past that we can rewind, pause, and fast-forward at will. We can witness a galaxy collision from a billion different angles or watch the very first stars ignite in the primordial darkness. But this incredible power is built upon a foundation of profound uncertainty. The entire simulation, and therefore our understanding of cosmic history, depends entirely on the initial conditions we feed into the machine at the very beginning. Every story demands a first page, but for the cosmos, that page is still missing. The initial conditions of the universe, the precise state of everything at the very first moment, are the ultimate historical cliffhanger. This is not a question of what happened immediately after the Big Bang, but what happened at time zero itself, the absolute origin point where our entire concept of time and physics shatters. At this threshold, known as the Planck epoch, our two most successful theories, general relativity and quantum mechanics, break down completely. General relativity, which beautifully describes the cosmos on large scales, predicts an infinitely dense and hot singularity, a point where its own equations fail. Quantum mechanics, which rules the tiny quantum world, cannot handle the extreme gravity of such a state. It is as if the cosmic historian picked up a pen to write the first word, and the pen itself dissolved. To understand the first page, we need a theory of quantum gravity, a unified framework that does not yet exist. In this void of knowledge, physicists propose breathtaking ideas. One profound proposal is the Hartle-Hawking no-boundary universe. In this model, the universe does not have a sharp, singular beginning in time. Instead, think of the beginning of time like the North Pole on Earth. If you ask what is north of the North Pole, the question has no meaning. The concept of north breaks down. Similarly, in the no-boundary proposal, the universe is a closed surface without an edge, a smooth geometry where time seamlessly emerges from a space-like dimension. There was no before because time as we know it did not exist. Another compelling idea is the quantum bounce, which suggests our Big Bang was not a creation from nothing, but a dramatic rebound from a previous cosmic phase, a great contraction where a prior universe collapsed in on itself before bouncing back out. These theories attempt to solve the deepest historical riddle of all. Why did the universe start with those perfectly tuned initial conditions? Why was it so exquisitely smooth, so flat, and set with that incredibly low entropy that gave time its arrow? This fine-tuning seems too perfect to be mere chance. One possible explanation is the multiverse. In a vast landscape of countless universes, each with random initial conditions, we simply find ourselves in the rare one where the settings were just right for galaxies, stars, and historians to emerge. Alternatively, there may be a fundamental, yet undiscovered, law of physics that mandates these specific starting parameters. The first page of the Cosmic Chronicle is its most important entry, the founding document that made all subsequent history possible, and we are still deciphering its faded script. This fundamental uncertainty forces us to ask what time even is. If its own beginning can be so elusive, our most intimate experience of reality might be the grandest illusion of all. We feel time flowing from a fixed past through a fleeting present into an open future. But what if this river is a mirage? Physics is now grappling with the radical possibility that time is not a fundamental ingredient of the universe, but something that emerges from a deeper, timeless reality. Think of temperature. We feel it directly, but it is not a fundamental property. It emerges from the frantic, invisible jostling of countless molecules. In the same way, the flow of time could be a collective, large-scale effect arising from a more basic, timeless substrate. This idea dismantles the very stage upon which we believed history was built. One of the most profound expressions of this is the Wheeler-DeWitt equation, a cornerstone of canonical quantum gravity. This framework attempts to unite Einstein's general relativity with quantum mechanics. and its most startling feature is that the variable for time completely vanishes from the core equation. The universe, in its most fundamental description, is static. It simply is. There is no external clock ticking outside the cosmos, no master timekeeper against which events unfold. So where does our powerful, undeniable feeling of time's passage come from? It must be generated internally by the changing relationships between the physical things within the universe. The tick of a clock is not measuring some universal flow. It is just correlating its own internal state with other processes, like the Earth's rotation or the vibrations of a crystal. Your experience of cause and effect, of one event following another, is a story the universe tells itself from the inside. This leads to the concept of the block universe, a single, four-dimensional structure where the past, present, and future all equally exist. In this view of eternalism, the Big Bang is not a receding event. It is a fixed location in the space-time block. The birth of the sun is another fixed point, and your reading of this sentence is yet another. The entire history of the cosmos is a single, frozen sculpture. We do not move through this block, we simply are extended along it, with our consciousness creating a moving spotlight we call the present. If this is true, then the universe is not actively building its history moment by moment. The entire chronicle is already written, complete and unchanging. The feeling of building, of becoming, is the emergent phenomenon, an intricate dance of information and correlation that gives rise to the story of change from within a timeless whole. This directly challenges our deepest intuitions about cause and effect. How can one event cause another if both are eternally fixed in the cosmic block? The answer may be that causality itself is an emergent property, a useful narrative woven by the universe to make sense of the intricate, pre-existing connections within the block. The universe's method of self-historicization would then be a magnificent, consistent illusion, a timeless reality giving rise to the powerful and beautiful story of time. The smooth, continuous flow of time is a compelling illusion. Beneath the surface of reality, history might be constructed from a vast collection of discrete, indivisible moments, like the individual frames of a movie. This is the radical proposal of Causal Set Theory, a framework that reimagines the universe's history not as a flowing river, but as a sprawling, intricate network of cause and effect. At its heart is a profoundly simple idea. The cosmos is built from a finite number of fundamental events, and the only thing that truly matters is which event caused another. Think of the entire history of the universe as an unimaginably vast social network. Each point or node in this network is a single atomic event, something as minute as the collision of two particles or as grand as the explosion of a star. The connections between these nodes are not friendships, but the immutable arrows of causality. One event causes another, and that connection is the most fundamental fact of their existence. Physicists like Raphael Sorkin champion this view, suggesting that the seamless continuum of spacetime we experience is not fundamental. It emerges just as a smooth digital image emerges from a finite collection of pixels. In this theory, there is no background stage of space or a universal clock ticking away. There is only this ever-growing web of causal relationships. The entire past and future of the cosmos is encoded in the architecture of this network. The order of events is not dictated by some external time parameter, but is defined entirely by their place within the web. If event A can send a signal to event B, then A comes before B in the history of the network. This creates a purely relational history, a story whose plot is determined solely by the internal links between its countless characters. The richness of the cosmic chronicle, then, depends on the complexity of this causal set. A sparse, simple network with few connections would represent a barren, uneventful universe. But our reality, with its galaxies, life, and consciousness, requires an immensely dense and intricately connected web, where a single event can have countless descendants, spawning chains of causality that weave together to form the complex tapestry we see. So how does this discrete, digital-looking network produce the smooth, continuous reality we move through every day? The answer lies in a process akin to zooming out. When you look at a photograph in a newspaper up close, you see the distinct, jagged dots of ink. But from a normal distance, those dots blend seamlessly into a smooth image. Causal Set Theory proposes that our experience of smooth spacetime is that zoomed-out view. The fundamental grain of reality is so fine, the network of events so unimaginably dense, that it appears perfectly continuous to us, just as a movie appears to flow smoothly despite being made of separate frames. This emergent reality is the continuum limit, where the fundamental discreteness of the causal set gives way to the familiar, continuous laws of general relativity on large scales. The universe's history, therefore, is this dynamic, growing network itself, a story written not in the language of time, but in the pure, minimalist grammar of cause and effect. If the universe builds its history link by link, what does that imply for the very nature of a single moment, and could those moments hold their own secret structure? The precise settings of our universe feel almost too perfect to be an accident. The force of gravity, the mass of an electron, the amount of dark energy, each one is dialed to an exact value that allows for a cosmos rich with galaxies, stars, and planets. If any of these fundamental constants were even slightly different, the story would have ended before it began. This is the puzzle of fine-tuning, and it points toward a profound explanation known as the Anthropic Principle. At its simplest, the weak Anthropic Principle observes a straightforward truth. The universe we observe must be compatible with our existence as observers. We could not possibly find ourselves in a universe where the constants forbid atoms or stars, because such a place would have no one to do the finding. This is a selection effect, a cosmic version of a survivor looking around and wondering why the environment is so perfectly suited for survival. The principle gains its real power when combined with the multiverse. If a vast, perhaps infinite, ensemble of universes exists, each with its own random set of physical laws, then it is no surprise that we inhabit one of the rare gems where the numbers lined up just right. In most universes, the nuclear forces might be too weak for carbon to form, or dark energy might be so strong that space rips apart before the first star ignites. Those universes are silent, empty, and brief, with no history to speak of. Our universe is not special because it was designed for us. It is simply one of the few where a long and complex chronicle could be written at all. Consider the specific example of carbon, the fundamental backbone of life as we know it. The creation of carbon inside stars depends on a seemingly miraculous coincidence. In the triple alpha process, 3 helium nuclei fuse to form a carbon nucleus. This process relies on a precise resonance, a perfect energy level within the carbon nucleus that allows the fusion to occur efficiently. If the strong nuclear force were just a few % stronger or weaker, this resonance would disappear and stars would produce very little carbon. Without carbon, there would be no chemistry complex enough to lead to planets, oceans, or living organisms. The universe would be a sterile expanse of hydrogen and helium. Our cosmic history, filled with stellar alchemy and biological evolution, hinges on this and many other delicate balances. From this perspective, the universe's magnificent architecture for history is not a universal given. It is a local condition, a fortunate set of bylaws in one particular cosmic neighborhood within an immeasurably larger meta-reality. The fact that we can trace a story from the Big Bang to conscious life is not a predetermined miracle, but the inevitable outcome of a probabilistic filter. We are here because this is one of the places where a story could be told. So does this revelation diminish the significance of our history, or does it make it more astonishing? If ours is just one tale in an infinite library of silence, then every galaxy, every fossil, and every thought becomes infinitely precious. Our ability to read the cosmic chronicle is not a minor footnote, but a rare and beautiful flowering of the cosmos's potential for meaning. Perfect symmetry is a kind of silence, a state where nothing can truly happen because every direction is the same. Our universe began in such a state, a realm of pure potential where the fundamental forces were unified as one. The entire history we have traced is the direct result of that perfect state breaking over and over again. Think of a perfectly symmetrical ball balanced on the absolute peak of a needle. It is poised, motionless, and full of potential energy, but it has no story. The slightest breath of air, the tiniest quantum fluctuation, will cause it to fall. In that fall, symmetry is broken, a specific direction is chosen, and a narrative is born. The ball is now rolling down a particular path, and its story has finally begun. The cosmos did exactly this. Its grand narrative unfolded through a series of cosmic phase transitions, moments when the underlying symmetry of reality itself shifted, releasing immense energy and writing new rules into the fabric of existence. The first of these great breakings may have been the grand unification transition. In the universe's first unimaginable fraction of a second, the strong nuclear force, which binds atomic nuclei, was likely unified with the electroweak force. This was a state of perfect but unstable harmony. As the cosmos expanded and cooled, it crossed a critical threshold. The unified force could no longer hold itself together, and it broke. The strong force split away, becoming distinct. This breaking released a colossal amount of energy that may have driven the period of cosmic inflation, violently stretching the fabric of space and planting the seeds for all future structure. Later, another pivotal transition occurred. This was the electroweak phase transition. Before this moment, the electromagnetic force, which gives us light, and the weak nuclear force, which governs radioactive decay, were a single, symmetric entity. Particles like the W and Z bosons, which carry the weak force, were massless, just like the photon, the particle of light. But as the universe cooled further, it fell through another symmetry breaking. This was the work of the now famous Higgs field. As the universe cooled, this field shifted into a new state, like water freezing into ice. In this new state, the W and Z bosons began to interact with the Higgs field, and they became massive. This single event is why the weak force has such a short range, and it is the reason atoms can exist at all. If the weak force carriers had remained massless, the universe would be a very different place, and the delicate nuclear processes inside stars might never have ignited. Each of these symmetry breakings introduced new properties, new particles, and new laws. They were the moments when the universe chose its specific plot, adding new characters and new possibilities to its unfolding story. The specific pattern of breakings in our cosmos, the particular path our universe fell along, is a fundamental part of its historical identity. It is what distinguishes our story from the countless other narratives that could have been written in a multiverse of different possibilities. The universe fell from perfect symmetry into the rich, complex, and structured reality we see today. But how can we possibly find evidence for these ancient, cataclysmic transitions that occurred in the first moments of time? We search for cosmic fossils, relics frozen in from those early epochs. One of the most sought after of these relics is a magnetic monopole. In our everyday world, magnets always have two poles, a north and a south. You can break a bar magnet in half, but you will always get two smaller magnets, each with its own north and south pole. A magnetic monopole would be a particle that is just a north pole or just a south pole, a solitary magnetic charge. Most grand unified theories predict that these exotic particles should have been created in prodigious numbers during the first symmetry breakings. Their stubborn absence today is itself a profound clue, telling us something crucial about how that early phase transition unfolded. Finding just one would be like discovering a fossilized bone from the very first chapter of creation, direct proof of the universe's dramatic fall from symmetry. These cosmic fossils are the ultimate primary sources, the original documents from the universe's birth. The most spectacular of these relics is the cosmic microwave background radiation. This is not a theoretical ghost, it is a real, tangible signal that fills every cubic centimeter of space, a faint whisper of heat left over from the Big Bang itself. When you tune an old television to static, about 1% of that snowy mess is the CMB, the literal afterglow of creation. This radiation is a baby picture of the cosmos, captured when it was just 380,000 years old. Before that moment, the universe was a searing, opaque plasma, too hot for light to travel freely. As it expanded and cooled, it finally became transparent, and that first flash of light has been traveling ever since, stretched by the expanding cosmos into the microwave frequencies we detect today. The precise patterns in this radiation, the tiny temperature variations that look like static to the untrained eye, are a frozen imprint of the quantum seeds that would one day grow into the entire cosmic web of galaxies. It is our most direct window into the primordial past, yet there are even more exotic fossils predicted by our theories, relics that have so far eluded our grasp. Magnetic monopoles are one of the most tantalizing. In our everyday experience, magnets always come with two poles, a north and a south. But most grand unified theories insist that in the universe's first moments, solitary north or south poles should have been created in abundance. These particles are like the dinosaur bones of the grand unification epoch. Their profound absence today is a historical clue in itself, telling us that the early universe must have undergone a specific kind of phase transition, like a supercooling that prevented their overproduction. Their continued non-detection helps us rule out entire classes of theories about the universe's infancy. Another theoretical fossil is the cosmic string. These are not strings in space, but defects in the fabric of spacetime itself, unimaginably thin filaments of concentrated energy left over from early symmetry breakings. A single cosmic string, thinner than a proton but stretching across the cosmos, would possess the mass of a mountain range. Its gravitational influence could warp the light from distant galaxies, creating double images, and its vibrations would ripple spacetime with gravitational waves. Finding one would be like discovering the original scaffolding used to build the cosmos. Then there is the dark matter that holds galaxies together. The leading candidates are WIMP, weakly interacting massive particles. These are not just invisible stuff, they are likely frozen relics from the first second of the universe. As the cosmos expanded and cooled, these particles would have stopped interacting with normal matter, freezing out from the primordial soup to become the gravitational backbone of everything we see today. Detecting a WIMP would be like holding a piece of the universe from its very first heartbeat. This grand cosmic dig, searching for these primordial artifacts, is how we constrain our theories of everything. The absence of monopoles shapes our models. The specific patterns in the CMB confirm the inflationary paradigm. The hunt for WIMP and cosmic strings drives billion-dollar experiments. These relics are the hard evidence, the physical connections to eras of unimaginable energy that we can never recreate. They are the ultimate historical constraints, proving that the universe's story is not just a fable, but a chronicle written into its very fabric. And this entire magnificent library, from the CMB to the rarest particles, faces a single, inevitable enemy, the same force that made its history possible. The final chapter of the universe is a story of forgetting. Billions of years from now, the last stars will flicker out, leaving the cosmos in a perpetual, deepening twilight. This is the era of degenerate remnants, where the cold, dark cinders of stars, white dwarfs and neutron stars, slowly cool against the backdrop of an ever-expanding void. For a time, these stellar corpses will be the only landmarks, the final monuments to a once vibrant galactic history, but even they are not permanent. Over trillions upon trillions of years, the relentless pull of gravitational radiation will cause orbiting stars to spiral inward and collide, occasionally sparking a final, fleeting supernova in the darkness. The galaxies themselves will evaporate, their stars drifting apart like a dispersing crowd, lost to the infinite stretching of space. Eventually, the universe will enter the age of black holes. These gravitational behemoths will become the sole curators of mass and information, the final chapters in a story with no readers. Yet, as Stephen Hawking discovered, black holes are not eternal. They slowly radiate away their mass, a process so slow that the largest among them may take a googol of years, that is a 1 followed by 100 zeros, to finally evaporate. In a final, silent flash of Hawking radiation, each black hole will vanish, returning its captured energy to the universe. With their disappearance, the last organized structures in the cosmos will be gone. What remains is the heat death, the state of maximum entropy. In this ultimate equilibrium, the temperature of the entire cosmos approaches absolute zero. Energy is perfectly, uniformly distributed. There are no hot spots or cold spots, no hills or valleys in the energy landscape. Every corner of the universe is identical to every other. In such a state, no work can be done, no engine can run, no complex structure can form, and no event of any kind can occur. The cosmic clock, whose ticking was driven by the flow of energy from high concentration to low, has finally, irrevocably stopped. This has a devastating implication for the universe's historical record. All those layered archives we have explored, the geological strata on dead worlds, the fossilized structure of the cosmic web, the chemical fingerprints in ancient stars, even the information encoded on the holographic boundary, become functionally meaningless. With no energy gradients to drive a computation or an observation, that information becomes inaccessible. It is a library where every book has turned to dust, and there is no one left to read them even if they remained. The history is still there, in principle, but it is lost in a sea of perfect sameness, its narrative erased by the ultimate uniformity. The universe's magnificent project of self-historicization, which began with a burst of low entropy and unfolded over billions of years of glorious complexity, was always a temporary phenomenon. The architecture of time itself, which seemed so solid and directional, ceases to have any meaning in a universe without change or causality. The past becomes a fossil without a present to contrast it against. This finality casts the entire cosmic epic in a poignant, ephemeral light. Our universe appears to be an architect building magnificent, intricate cathedrals of memory, knowing full well they are made of sand, destined to be smoothed away by an inevitable tide. This leads to a final, desperate question. In the face of this absolute end, is there any conceivable way for the universe's history to be preserved, for its story to escape the silent fate of heat death. In the unimaginable stretches of deep time, the universe's own laws might engineer a paradox more bizarre than any fiction. The Boltzmann brain thought experiment emerges from the cold statistics of an eternal, high-entropy cosmos. In a state of near-total equilibrium, random quantum fluctuations will still occur. Given enough time, an astronomically long but finite period, the jostling of particles could spontaneously assemble a fully formed, self-aware brain, complete with false memories of a past that never existed. According to pure probability, in a universe lasting forever, it is statistically more likely for such a disembodied consciousness to flicker into existence than for an entire, ordered cosmos like ours to evolve naturally. This idea pulls the rug out from under our entire understanding of history. How can we trust our memories of galaxies and dinosaurs if we might just be momentary flukes, isolated minds hallucinating a grand narrative in the void? It is the ultimate skeptical challenge to the reality of the cosmic chronicle we have traced. Yet this terrifying prospect is counterbalanced by an equally radical hope. The final Anthropic Principle pushes this logic in the opposite direction. It suggests that if intelligent life is a necessary part of the cosmos' long-term story, then it might eventually develop the power to influence the universe on a cosmological scale. A sufficiently advanced civilization facing the creeping onset of heat death could conceivably find a way to reset the cosmic clock through technologies beyond our imagination, perhaps manipulating the fabric of space-time or engineering a new Big Bang. Intelligence could trigger a cosmological resurrection. The universe's history would not be erased, but perhaps carefully archived or even used as the seed for a new cycle of creation. In this speculative vision, we are not passive victims of entropy, but potential stewards of cosmic memory, the means by which the universe ensures its story continues. These two extremes, the Boltzmann brain and cosmic resurrection, represent the outer limits of our current understanding. One reduces our history to a fleeting statistical illusion, while the other elevates our potential to become co-authors of a cosmic rebirth. They force us to confront the deepest questions about the narrative we are part of. Is our universe's magnificent biography a singular, precious event, or is it just one act in an endless and sometimes absurd cycle of formation and dissolution? While these ideas reside on the fringes of theoretical physics, they are vital thought experiments. They stretch our conception of reality to its breaking point, reminding us that the final chapters of the universe's story are still unwritten, and that our role in it may be far stranger and more significant than we have yet dared to dream. With all this profound knowledge laid out before us, from the first quantum flicker to the last possible thought, how does it reshape our view of our own fleeting moment within this grand, self-writing epic? Our journey through time's secret architecture reveals a universe that is not a silent, empty stage but an active, dynamic author of its own epic story. We have traveled from the seething quantum vacuum to the great cosmic web, from the nuclear forges of ancient stars to the emerging digital nervous system of our own technosphere. At every scale, we found the same profound process at work, reality meticulously inscribing its past into the very fabric of existence. The ultimate takeaway is both simple and staggering. History is not something that merely happens to the cosmos. It is a fundamental process the universe performs, an intrinsic feature of its being, as essential as gravity or light. While the distant future may hold the silent, cold fate of heat death, that eventual quiet cannot erase the profound wonder of the present moment. The fact that a universe of pure physics can generate such rich, complex, and even self-aware narratives is a miracle in its own right. This understanding invites a new way of seeing. The next time you stand under the night sky, look up and see not just a random scattering of lights, but a living, breathing history book, its pages open and its story still unfolding with every passing second. We are all part of this ongoing chronicle. We would love to hear your thoughts on this, the grandest of all stories, in the comments below. And if you are eager for more journeys into the heart of cosmic mystery, be sure to subscribe.